So now let's define one of the laws of nature, the first law of thermodynamics. There are several different ways that we can state the first law of thermodynamics, but one of the most technical ways to state it is that the total energy change, delta E, of a system is equal to the heat absorbed by the system plus or the heat absorbed or lost by the system, plus the work done on or by the system via the surroundings. Oh, what a lot of prepositions, right? So the heat absorbed by the system or lost from the system, plus the work that is done on it or by it via the surroundings. All right, so we are going to have to try to think about what that means for a little while here, and that's what this lecture is going to be about. A simpler way of thinking about the first law of thermodynamics, since there are a lot of different ways of thinking about it, is just that the energy of the universe is constant. Remember that the universe is the system plus the surroundings. And what this essentially is saying is that energy can neither be created nor destroyed. Okay, this is conservation of energy. It's always going to be going somewhere. So if the system is losing energy, if heat is being lost by the system, it must be going into the surroundings. If the system is gaining energy, it must be coming from the surroundings because energy can neither be created nor destroyed. Okay, let's get a little bit more technical. Internal energy. Okay, so the internal energy, when I say internal energy, it means of a system. So the energy that a system contains. Internal energy is a state function, capital letter E, and like all state functions, we can calculate delta E by looking at the difference between the final state and the initial state, subtracting the energy of the initial state from the energy of the final states. And here, the initial and final energies are functions of the potential and kinetic energies of the system. We're not going to go too much into potential and kinetic energies here. You probably have heard about potential energy and kinetic energy before. Potential energy is stored energy, kinetic energy is energy of motion. So we're kind of looking at both in internal energy. We're looking at all of the energy in the system. So we can't measure the absolute internal energy, but we can look at the changes in internal energy. So only delta E can be measured, not E by itself, but delta E. And we can measure delta E through two types of energy changes, heat and work. So here we're going to explain a little bit more of that first law of thermodynamics. Heat is not a state function. It has a lowercase letter, and we denote it with a lowercase letter q. And here we're interested in whatever heat is absorbed by the system or is lost by the system. So we're looking at heat that's either absorbed or lost by the system from or to the surroundings. Work is also not a state function. We denote it with a lowercase w. And work is defined as we talk about work. Let me just say, give you the prepositions first. Work that's done by the system or done on the system. So the work done on the system or by the system vis-a-vis the surroundings. And to define what work is defined as a force acting on a distance or over a distance. So whenever you see force times distance, that's what work is. Okay, so work equals force times distance, F times D here. And the easiest way to think about work is that it's kind of a catch-all energy category. It includes all forms of energy other than heat. So I like to just think about it as a catch-all, all forms of energy that are not heat can kind of fall into that work category. So it's very important to consider both the magnitude and the sign of heat and work. So I want to devote a few minutes here to explaining sign conventions for heat and work. It's extremely important to understand these so that you can do your arithmetic correctly. So we have positive values. Everything is from the point of view of the system. So positive values, so these are sign conventions for both heat and work that I'm defining for you right now for both Q and W. Positive values are when heat is transferred into the system from the surroundings. So when heat goes into the system from the surroundings, then that Q value would be positive because it's from the point of view of the system. And again, this is purely a convention, and you need to just understand this definition. There's nothing natural about it. It's just a convention that you need to understand. From the point of view of the system, work, W, is going to be positive when the work is done on the system by the surroundings. Conversely, you have negative values for heat and work. Again, it's from the point of view of the system. So when heat is lost by the system to the surroundings, then that Q value would be negative. If the work is done by the system on the surroundings, then that W value would be negative. Okay, so when the work is done by the system on the surroundings, the W value is negative. So the easiest way to remember it is that the sign conventions are from the point of view of the system. So using these sign conventions, we can figure out the change in internal energy because delta E is equal Q plus W is equal to Q plus W. The internal energy is equal to heat plus work. This is our master equation here for the first law of thermodynamics. Notice we have a capital letter for E. That's a state function. But the Q and the W, the heat and the work, these are lowercase letters. These are called path functions. Lowercase letter functions are called path functions because we can't just take the delta of them by subtracting the initial state from the final state. The path that is taken is very important. The units of all of these functions, energy, heat, and work, are joules usually. I mean, there's lots of different units you can use for energy, but joules are the one you're going to see most frequently, and you can scale it up, for example, to make a kilojoule. You should know that 1 joule is equal to 1 kilogram meter squared per second squared. So you can do some unit conversions. All right, so how do we use this? Let's do just a quick example. Calculate the change in internal energy when a system releases 20.8 kilojoules of heat and 6.2 kilojoules of work is done by the system. Very simple problem here. Really, we're just trying to learn the sign conventions. So we're releasing heat. It's from the point of view of the system. So when the system releases heat, that is going to be a negative Q, a negative heat flow. So the Q value is going to be negative. Okay, maybe it's actually going to make more sense. We're going to have a negative value for Q. Now, what about the other one? Work is done by the system. When work is done by the system, that is also going to be a negative value for work because, again, it's from the point of view of the system. So delta E is equal to Q plus W. We're looking for the internal energy of the system. That Q value has to be negative because the system is releasing heat, so that's a negative flow. And we're going to also have a negative value for work. So overall, the delta E is going to be minus 27.0 kilojoules for this example.